Stop.
I don't see your video. Your
No.
video is, is stuck. I only hear you.
The camera is on. Let's try to restart the camera. It's reported on my camera.
Okay.
Can you see my screen now?
Not yet. Maybe try to disconnect and connect again to the meeting. I saw you earlier better.
Okay, so I'm trying to disconnect and reconnect. Can you see me now?
No, I didn't see that you were reconnected. Let me remove you and try again. Hi everyone, we'll start in a few minutes. Okay, now I see your video.
Okay.
And I see you.
Let's try the share.
Try the share. Okay, I see something. Okay. Okay. Okay, so hi everyone. We are here to have an overview on the RegCM, Regional Climate Model. We have here Graziano from ICTF.
ICTP.
Sorry, ICTP. Sorry, and just go ahead. Introduce yourself and go ahead.
So welcome everybody. What I'm going to talk about is the regional climate model RegCM. Is an Earth system model, atmospheric and land component that's able to produce physical downscaling of IPCC GCM scenario simulation. So first, what is ICTP? So ICTP is a UNESCO, so United Nations Education and Science and Culture Organization, class 1 institute. So we are part of the UNESCO, and we are devoted to science. So it was founded in Trieste, in Italy. And what we do is we do international cooperation through science. We have a number of research section in ICTP, and we have the Earth System Physics section. We, as ICTP, have a lot of activities where people come in visit Trieste, or we organize activity in developing countries. We have, together with the Italian Institute, which is a superior school for, so the equivalent for the Italy of a high-level PhD level school, we have this Master in High Performance Computing. This Master in High Performance Computing is a post-master school for PhD level students, where we provide high performance computing teaching. So let's get back to the Earth system model. So what is an Earth system model? An Earth system model is a solver for the equation for atmosphere, ocean, land, everything. So that's simulating the Earth. In terms of dynamics, what we have the Navier-Stokes equation, and what the model does is use this equation to integrate in time and get to the evolution of the fluid essentially above the Earth on a grid. Why we do this? We have seen this also yesterday for the case of the icon model. So what we do is to get out of this climate scenario simulation. The UN IPCC, International Panel on Climate Change, has a World Climate Research Program, WCRP, and in the framework of this program, the scientists has agreed upon running common experiment among all the institutes doing climate research in the world to simulate what will be the future following what are called shared socioeconomic pathways. So scenarios of projected socioeconomic global changes up to the end of this century, and to have atmospheric ocean models, global ones, and then we'll see also regional ones, simulate what will be the future, changing only the concentration of the greenhouse gas emissions. A regional model is in the line of climate models, but we are working on a limited domain. So what we provide to a regional model are the boundary condition coming from a global model. For example, we have seen yesterday again the icon, which is a global model. A regional model gets this boundary condition from a global model and performs the time integration, so the physical downscaling. So we work at higher resolution we compare to the global model on a limited domain, where we discretize the numerical equation and we solve those for the time evolution using the same radiation boundary condition. So the greenhouse gas concentration has been used by the global climate model. In this way, we are able to obtain a higher resolution information, which contains also the added value that comes from a higher resolution topography and higher resolution description of the surface. And we can use obviously, because we have less computation to do, because we don't work global model, we can use more physics to parameterize the phenomenon that happens at a lower scale. We couple this with the information coming from the description of the surface. So we have also a coupled model that describe the interaction with the vegetation, with the surface, with the hydrological cycle. And the model can be also coupled with other models, for example, for the ocean, the cryosphere, the transport and the chemistry for aerosol, the river routing, the wave model. What we are talking now is just the atmospheric and the land component. But for this experiment, we will use just the atmospheric component. There are good things that comes on a regional model approach. So we do a physical downscaling. So we have the equations and we can do a we have a comprehensive climate model system, so we have all the pieces to describe the Earth environment. It can be used in because we have the equation, so we can use in a wide variety of applications to do process study, paleoclimate, climate change, seasonal prediction. And we have this high resolution, we can go very high resolution through multiple nesting of different resolution from the GCM. We have seen for ICON that global model aim to reach a very high resolution, but this is a task that most probably will be possible only not with the current exascale system, but most probably with the next generation exascale system. So regional model are something like a gap filler for now for downscaling the low resolution climate model, global climate model, on a very high resolution grid. There are anyway some drawback in doing physical downscaling, and mostly is coming from the fact that we need computational resources. So it's not free. And this more or less the same level of computational resources are required for a regional model working at very high resolution than it's required for a global model run. The ICTP RegCM is one of the, if not the oldest model. What we have is the code base contains as of yet still pieces that comes from a work in the NCAR from Filippo Giorgi, which was up to the end of the past month the head of the Earth System Physics section here at ICTP, and he has now retired from the end of the 80s. So some part of the code is down to NCAR code in the end of the 80s. It has obviously evolved in time, and the most recent version is now, you can find the code on the GitHub, and is from, it's described in a paper of George et al. Of this past year. What we do with this is participate in a coordinated downscaling experiment project founded by the, not founded, but coordinated by the World Climate Research Program. And the output of the model are used to assess the regional scale climate change in the advancement report of the IPCC, which are the basis for the scientific basis upon which you may have heard in the news this COP meetings where the government in the world meet to decide the action to be taken to mitigate climate change. Those actions are based upon scientific results that come from modeling and also from the regional models. So the code base is in Fortran. Fortran is a very old language. Is a language that where the basis of the language is in the 50s also. But it has evolved and it's still evolving. There ISO group that's evolving the language, putting into it the modern concept up to object-oriented. The good thing of the language is that the array is a first-class object, so you can perform array operation element by element with just one line. And mostly because historically this is has been used for scientific computing, We have a lot of high-level, high-quality compiler for the Fortran language. A lot of the numerical libraries that are used by a number of scientific software packages are written in Fortran, or at least until the last iteration were written in Fortran, even though there is now a push to rewrite those libraries by using more say compliant for the integration languages. But anyway, you have access using Fortran to a lot of numerical libraries. You have interfaces, native interfaces for MPI, so message passing interface, and this is what the RegCM model uses for parallel communication. There is also in the Fortran language a parallel standard, namely coarrays is named, that should enable, when it will be implemented by vendor compiler, it should allow a transparent language supported communication layer, but still this is to be coming. The good thing in terms of integration, so for Fortran, is that at least in the latest upcoming NVIDIA compiler, part of the Fortran standard should allow the compiler to generate parallel code that can be sent directly to the accelerator using, for example, for loop, do concurrent syntax that should split this and send it to the automatically through the compiler to the accelerator. Okay, the worst thing that we have in our code is that this is an atmospheric code, and in the equation we have what is called the advection. So we have flux that's transporting stuff, and in principle, to describe this, you cannot work with locality, strict locality, but you need information coming from surrounding element. So what is going down to is that this is an infamous stencil code. So you have a class of class of kernels that update the array element using a fixed pattern. So to compute the value of the variable in a point x, y, so in EJ, using the indexes of the horizontal discretization, you need the nearby. The nearby, that this, depending on the order of the solver, you need more and more nearby point. This forces a problem because this forces communication. So every time integration, part of the information local to a processor must be communicated to other processors. Then there are a lot of tricks to reduce the amount of time of information that must be communicated, or the frequency with which this must be communicated. In RegCM, what we have a patch library that handles this synchronization, and it is based on the MPI. So we have MPI calls, and this will be a part of your task. It will be to identify the MPI, the most used MPI calls that are embedded, hidden in the communication layer of the model. Another important thing is that the netCDF I/O layer, you will see only for this task that you have to accomplish only the output layer of the RegCM, because we are using not the full capability, so we are not simulating a real case, but we are using a periodic boundary condition box model, which it is initialized with a constant vertical profile of atmospheric status variables. But you will see the output layer. So the model writes output data, and these output data are written in this netCDF format. The netCDF format, it is a standard format for the atmospheric and climate community. You have seen also yesterday that ICON model writes the data using this netCDF format. The good thing is that to access netCDF files, you have the choice. You can choose almost any programming language, and you will have an interface for reading this netCDF file. And the good thing is that the metadata that describe what are the variables that you need to measure, the relationship in between the variable, are written inside the file and can be accessed using an API. The good thing is that also that if the hardware support this, the netCDF allows also for parallel write and the compression also of the data that are the arrays that are written using filters that supports a number of modern compression algorithm. The bad thing is the scalability. So as you see here in this graph, that the model increasing the number of nodes, keeping constant the domain size, has a limit in the scalability. So you see here in this curve that increasing the number of nodes at the beginning provides a very nice curve, but after a while the incremental gain that you have in doubling the number of nodes is you may have in doubling the number of nodes is very reduced. So you can get very small advantages in increasing the number of nodes that you throw at a problem. Moreover, at some point you will reach the state in which increasing the number of nodes decreases the computational effort so much that the communication part of the MPI is taking more time than the computation itself. The task that you have to do. So let's get back to the task that you have to do is based on the radiative convective equilibrium code. So you have to initialize, the model initialize the internal status with a fixed profile, adding a small initial perturbation to break the symmetry. So that convective plumes will start to appear because the surface temperature is kept constant, and the convection will start here and there on the domain. What you have to do is following the very simple steps that are described in the on the Confluence site, is to compile and run this simulation and to profile and identify the most used MPI calls that are in the code. For this, you can use any tools that you can find on the cluster that you have access to. What you have to do is to visualize and plot the netCDF file output results. We have seen yesterday, for example, for icon, that you can do that on using 3D visualization. Some of those fields are defined on a three-dimensional grid, and you can, for example, think of plotting the cloud structure, so the different kind of clouds that the model creates, and see the time evolution of that, maybe changing the point of view in a 3D movie. I'm proposing also a bonus task, so to optimize one of the subroutines, this one of the modules. But this obviously will be limited to the people knowing the Fortran programming language, which is not frequently taught language in modern computing courses in academia. And the people knowing the Fortran languages are more or less getting wider as I am. The expected results. So what are you expected to do? You have to submit the simulation standard output by the running model. So the model, while it runs, it prints out something on the screen, or you can submitting using a submission queue, or you can get that in a file and send us that to the and that will to certify that you have been able to complete this task. And second step is to submit the profiler produced results. You can think also producing a small document, and you have to highlight which are the most called function MPI functions. And for the third task, for the visualization, you can produce a small video showing the time evolution of the physical system. You can do it 2D, or if you can, even the 3D fields. The bonus task, how for the previous bonus task, so how to optimize to send the optimized code. You can, for example, fork the Git repository and submit a pull request with optimized code for the subroutine. I've completed what I wanted to tell you, so I would accept questions, and if you want to, if you have questions for me.
Thank you so much, Giuliano. Anyone, if you have any questions, just feel free to say. I'll just mention that we will create a team folder for you, and you need to upload all the results to that. It's a OneDrive folder. I know it was a lot, so I don't know if the team already started experiencing with that. If you have any questions, just feel free. We also have the Slack channel for questions, so if you have questions later on, don't hesitate. If you're stuck, if you have some compiling issue, any other issues, let us know. Someone was writing from UPC.
Do you have any recommendation which software to use in order to visualize the result? So I would say that to visualize the results, so you can use the Python stack. For sure, if you know how to program in Python, there is a very nice library which is called Xarray that with a one-liner, you can load into memory a netCDF file. So there is a open data set, and you load that as a multidimensional data set. And then you can use any Python package to plot that. Another option may be ParaView. So the library is called Xarray. So I'm typing it in Xarray.
In the chat, yeah.
Yes. Or you can use ParaView. ParaView is a more complex graphical processing and 3D viewer. It does not directly read the netCDF as of it. You have first to describe somehow what you have into the netCDF. But there are tools available that can help you transform the netCDF into its own VTK format. Again, this can be done also with libraries joining Xarray to VTK. So from Xarray, I think it's a good entry point in Python to then attach to it any other, or you can write your own software to read. So because of the fact that for the API for netCDF, it's almost any programming language that you can think of. You can write your own in R, GNU R, or anything that's producing graphical output. Other questions? So, for example, also MATLAB, so the actual file format, if you enable, by default, it's enabled to write netCDF4. netCDF4 actually on disk is HDF5, and HDF5 it's actually the mat format. So it's you can you actually use MATLAB if you pay for that. Changing the compiler optimization flag. Obviously, this is actually not required to optimize the code, but if you want to show that the optimization that you can, for example, it will be evaluated positively, that you can enhance the performance from the basic run. So if you are able to optimize particular with using particular optimization flag on the platform on the HPC cluster you have access to, it will be good to know. The configure script, because this is based on for the compiling the code, you will be using a configure script. Supports you, helps you set up optimization flag for some so for at least for x86 64 for most of the compiler. Most recently, it's not in the branch that you are supposed to use, but we have already some ideas for the IF, so the new Intel compiler. The NVIDIA compiler also should be supported out of the box, so you should just add which compiler you want to use. If you find that some optimization flag gives you higher performances on one of the cluster, it may help also if on that particular HPC platform, if any RegCM user it will be good to know for the or the admin of the sysadmin of the cluster how to better compile the code on the cluster itself.
Okay. Any other additional questions? Even if you have later on questions, just email us. Use the Slack. Better actually to use the Slack, but don't hesitate. Don't stuck. Just let us know, and we'll try to support you whatever we can. For the task, oh yeah, I see someone is lifting his hand. Jan.
Yes, can you hear me?
Yeah.
Yes.
Wonderful. Can I just ask, can we set up maybe separate channels for each application on the Slack so everything isn't on the main channel?
Yeah, we can do that.
Yeah, great.
We tried last year. It depends, but we can do that one channel per application that we can.
Yeah, just for like compiler problems or just scripting issues, just so everybody else doesn't get bothered with that sort of stuff.
Yeah,
okay,
I can help with that. So we can create those channels. You can use the main channel or the team channel, whatever you feel. We will. I'll see it, and we will find it. So we are here for you. So try to learn from that experience, and hopefully take it to you with you to your next level in the career. Anyone? Any additional questions? Okay, so I would like to thank you, Graziano, for the presentation. And again, we are here. Try to experiment. I know it's just a beginning, so you might have questions as you go, but don't hesitate. Contact us, and please join us in 20 minutes. Take a coffee or something. We have the next session with Neko. So make a small break, and we'll meet you soon. Okay, thank you, everyone.
Bye.
Bye.